Now let's take care of section 4.2, properties of rational functions. We'll look at graphs of rational functions, but we won't consider graphing of rational functions in this section. We'll consider that actually in the next section. Okay, so the plan is in this section to define rational functions and to find vertical, horizontal, and oblique asymptotes. Again, we won't graph this information in this section. We'll talk about where it occurs, and we'll take care of the graphing stuff of rational functions in the next section. So a rational function is a function that's of the form r of x equals p of x over q of x, where p and q are polynomials. Q is not the zero polynomial, the constant polynomial, which is equal to 0. In fact, some people don't even consider the constant polynomial equal to 0 as a polynomial. It causes some difficulties for the fundamental theorem of algebra. But it's a ratio. Rational, just as with rational numbers, are ratios of integers where the denominator is not 0. Rational functions are ratios of polynomials, the functions we considered previously, where the denominator is not the 0 function. If p and q have no common factors, then the rational function is said to be in lowest terms. So we cancel common factors with an appropriate level of care to be dealt with as we go through rational function material. But we cancel common factors in the numerator and the denominator. That's how you get a rational function in lowest terms. The domain of a rational function is, well, I'd look for what could go wrong. What could go wrong for us at this stage is square roots of negatives. Polynomials don't have any square roots, so neither do rational functions, and division by 0. But we do have the possibility of division by 0 in the event that the denominator is 0. So the domain of a rational function is all real numbers except those for which the denominator equals 0. And we could find those bad numbers by factoring. So as with polynomials, much of this will come down to factoring the polynomial in the numerator and the polynomial in the denominator. All right, we're going to add a function to our library of functions. The book, as it approaches lots of these functions, says by plotting points and based on symmetry and carefully analyzing the behavior near 0. For h of x equals 1 divided by x squared, a rational function, we find that it has a graph given in figure 25 here. So we'll consider this as a function added to the library of functions. So we could translate and stretch and compress this kind of thing and reflect. But notice there's symmetry with respect to the x-axis. Right, this is an even function, so it's got that kind of symmetry. When we put large x values in, we get out small y values. The bigger the x value, the smaller the y value on the left and the right. We'll say something about asymptotes here shortly, but this will certainly have an asymptote of y equals 0. And when we put in numbers close to 0, we square them and take the reciprocal. Squaring them makes them closer still to 0, and then the reciprocal makes the output large. So we're getting some type of vertical asymptote of the x-axis, the line, of the y-axis, the line x equals 0. So we will take as given that the graph of 1 over x squared has this general shape. And that'll be useful in dealing with rational functions in general, especially these ideas about asymptotes. So let's formally introduce asymptotes. Let R denote a function. Any function, of course, the plan here is that we're dealing with rational functions, but that's not a constraint in this definition. This is a little soft in details and mathematical details for reasons to be discussed shortly. If As x gets arbitrarily large in either the positive or negative direction, which we denote as x approaches negative infinity or x approaches positive infinity, the values of r of x approach some fixed number L, then the line y equals L is a horizontal asymptote of the graph. What does it mean to get arbitrarily large? What does it mean to approach this number L? Well, those are calculus ideas. So we have to leave this fairly informal in here. You will formalize all this when you can deal with the infinity symbol in a rigorous way, and you do that in calculus. And you'll deal with these in terms of some types of limits. For us, let's just make these pictures bigger. In figure 27, parts A and B, they're dealing with this horizontal asymptote stuff. So here's the line y equals L, and the idea is when we put in big X values, the graph of the function r of x is going to be close to the line L. Here, the graph of the r of x function will be close to the line L when we put in large negative x values. So we go to the left direction here, the curve gets close to the line y equals L. As we put in large positive x values here, the curve gets close to the line y equals L on the right-hand side. So these would be denoted. They've actually snuck some calculus notation in here. The limit as x approaches infinity of r of x equals L is what they've written in the little square brackets here. We'll avoid that notation with some regret. What exactly a limit means is a very involved idea. But it means you can make this curve as close as you want to the line y equals L, except you can't necessarily make them equal, by making x sufficiently large. So you tell me how close you want this curve to get to the line L. You tell me that first, and then I'll tell you how big you need to make x to have the curve that close. And from there on out, from there to the right, the curve will be that close and remain that close. And a similar discussion on the left-hand side. You tell me how close you want this curve to get to the line y equals L, and I'll tell you how far to the left you need to go, so that beyond that point, the curve will definitely lie within your desired positive distance of the line y equals L. Vertical asymptotes. Verbiage a little smaller. If, as x approaches some number c, the values, absolute value of r of x approach infinity, that is, either r of x approaches negative infinity or if r of x approaches positive infinity, then the line x equals c is a vertical asymptote of the graph of r, as illustrated in the right hand two pieces of figure 27. So what we have here is, here's the number x equals c. They've actually drawn the line x equals c is a dotted line because it's an asymptote. We'll normally represent asymptotes with dotted lines. And what happens is, here the claim is the limit as x approaches c of r of x equals infinity. So when we plug in numbers close to c, this limit idea involves closeness. When we plug in numbers close to c, we get out function values that are really big and upward. So positive and large. You tell me, how large would you like these function values to be? You tell me that, and then I'll tell you how close you have to get to c to have output values that big. Over here, the idea was, how close do you want to get? It was a closeness idea, close to the line y equals L. Over here, it's an idea of getting large. You tell me how large you want this to be. And then I'll tell you how close you have to get to c to make that function take on such large values. We can also have behavior like this. Remember, it was defined in terms of absolute value of r of x approaching infinity. Well, it could be the function goes to negative infinity from one side and positive infinity from the other. And we could have some behavior like this. Well, it's still a story of the function can be made as large as you want by plugging in numbers bigger than C, but close to C, and on the right-hand side of C to get the large positive values out. You can get large negative values out by plugging in X values close to C and a little bit on the left side, the negative side of C. They've used some one-sided limit notation in this, as well as the previous one, in fact. But what you need to take out of our conversation, because this is all we have, is horizontal asymptotes. The curve gets close to that horizontal asymptote, and it stays close to that horizontal asymptote for large X values, be it in the positive or the negative direction. When we have a vertical asymptote, the function gets really big near that vertical asymptote. For X values close to C, the function gets really big in absolute value. Maybe it goes up in both directions. Maybe it goes down in both directions. Maybe it goes up in one direction and down in the other. Still, the absolute value can be made large by making X close to C. In general, X equals C. I don't know what happens there. I might not even care what happens there in general, but with rational functions, and that's our problem, with rational functions, where you have these vertical asymptotes, the function will not be defined. So X equals C will be a vertical asymptote in both cases, and for rational functions, C is not in the domain of that function. All right, as I mentioned, we really need the idea limits to make this more mathy, to make it more than just looking at pictures. We're stuck with the pictures and accepting graphs that the book has given us in the library of functions. You take Calculus 1, Chapter 2, Section 6, so this is the first half of Calculus 1. You'll deal with limits involving infinity, and those types of limits, the notation the book has already used, those types of limits are what allow you to find asymptotes of graphs. A common misconception is the following: that an asymptote of a graph is something the graph gets closer and closer to, but never gets there. That's not what an asymptote is, especially not what a horizontal asymptote is. The idea really is, if you want an informal explanation of it, and that's all we've got at this stage, at least for horizontal asymptotes, is not closer and closer, but gets close and stays close. Maybe it does get there, and you can't get any closer than that. But the idea of a horizontal asymptote, to be elaborated on when you deal with limits in Calculus 1 in detail, is you get close to the horizontal asymptote and you stay close to the horizontal asymptote. Maybe you don't get closer and closer. Maybe you get closer and then you go away, but you don't go very far away because you stay close. Maybe you do get there. That's what a horizontal asymptote is. Quite informally, actually, look at my online notes, and there's a link to a little article I wrote for mathematics teacher back in the day, in the 90s. That elaborates on what horizontal asymptotes are in more detail. Sullivan, our book, says the graph of a function may intersect a horizontal asymptote. That's any function. Rational functions included. A rational function will intersect a horizontal asymptote only a finite number of times, but we can do some stuff where the function might intersect the horizontal asymptote an infinite number of times. That'd be a good thing to do with trig functions, not with rational functions. But it's not never gets there. And I can read Sullivan's mind on when he makes a statement like this. He's trying to address this closer and closer, but never gets there idea. It can get there. He doesn't really address it doesn't have to get closer and closer idea, at least not at this stage. Maybe it's further in the book, but that's the case as well. Closer and closer, but never gets there. That's not the definition of a horizontal asymptote. Now, with that said, many of the examples we'll see will involve closer and closer, but never gets there. Not all of them, but many of them will. And that's where, if you've seen this in the past, and I've even used that verbiage in the videos, the idea of closer and closer but never gets there. It does naturally arise in the setting of some rational functions, but not all of them, and the world ain't entirely made out of rational functions. So in the future, you'll deal with more sophisticated functions. And in calculus, you'll be able to spell this out a lot more clearly. But we're doing what we can. The book also comments the graph of a rational function will never intersect a vertical asymptote. I mentioned that earlier. If we have a rational function and a vertical asymptote, that function will not be defined at x equals c if it's a rational function. It could be some other kind of function, and it could have a vertical asymptote and be defined at x equals c. It'd probably have to be a piecewise defined function if it were such a thing, but that's possible. So there's, in terms of pictures, what asymptotes, horizontal and vertical, are, and a little warning about what they are not. There's a third possibility. Well, there's a bunch of other possibilities. There's a third possibility that we consider. If, as x approaches negative infinity or positive infinity, when I plug in big positive x values over here or big negative x values over here, the graph of a rational function r of x can approach a linear expression of the form ax equals b, where a is non-zero. If a is 0, it's a constant term, and we're dealing with a horizontal asymptote. But with ax equals b, we've got a line of slope a, where a is not 0 by the hypothesis, and the line y equals ax plus b is called an oblique asymptote or a slant asymptote of the rational function. Here's what we get in terms of a picture for an oblique asymptote. So we'd have some type of situation like this. Here's the line y equals ax plus b. And when we plug in, their suggestion here is when we plug in large positive x values, we're getting out function values that are close to this line. Maybe they equal this line, maybe not. But having this as an oblique asymptote means this function gets close to this line eventually, that is for x sufficiently large and on the positive side in this picture, and it stays close. It eventually gets close. You tell me how close you want it to get. You give me an arbitrary positive distance, and I can tell you the x value, if I know the function, for which at and beyond that point, the function will be that close to the line, at and beyond. That is, it gets that close and it stays that close as x moves to the right. And for a rational function, we'd likely have some similar behavior over here on the left-hand side. But they've just illustrated what happens is in their notation as x approaches infinity. That is, as x gets large in the positive direction, in the right-hand direction. So horizontal asymptotes, vertical asymptotes, and oblique asymptotes. Let's look at an example, number 30. From this section, says, consider the graph. Like I said, we'll graph in the next section. In this section, they've given us a graph, and they want us to dissect this graph. Find the domain and range of the function. Okay, that's easy enough if we got a graph. The intercepts, if any, easy enough if we got the graph. Horizontal asymptotes, vertical asymptotes, and oblique asymptotes. Okay, we can get all that stuff from the graph. Okay, we'll probably bounce around a little bit in the next slide and come back and look at the picture. But it says find the domain of the function. So for which x values is this function defined? Looks like over here, we're getting outputs for all these x values at x equals 0. Doesn't look like the function is defined. For x a little bit less than 0, function's defined. In fact, it's giving us out some large positive values, very indicative of a vertical asymptote. Not defined at 0. For x a little bit bigger than 0, it's giving out large negative values, but it's defined. And it's defined for all other x values. The indication that they've got the little arrow here and the little arrow here. I've complained about the graphs they give us in the past, but this one ain't so bad. And the fact that they put this dotted line in here. So they're indicating that oblique asymptote with the dotted line. So when x is large and positive, the graph will be close to this dotted line on the right. When x is large and negative, the function values will be close to the line on the negative side. So it looks like it's defined everywhere except at 0. That'll take care of the domain. Go look at the slide and write the answer down on the next slide. Range, what y values do you get out? Well, this looks like it's going upwards without bound. In fact, there's a dotted line here to indicate a vertical asymptote. So it's going in that direction. So we get all these y values out. In fact, we get them all out twice, once on this branch of the curve and another time over there, until we reach this low point of -1, 2. This looks like it is a minimum for the function, a local minimum for the function. And then there's no points on the curve that correspond to y values less than 2, down to 0, down to -2. And at -2, we reach a local maximum of the curve. And then below that, all y values are taken on. So the only x value for which the function is undefined in terms of the range is 0. As we observed, the domain is -∞ to 0, parentheses, union, parentheses, 0 to infinity. Everything except 0. We knocked 0 out with a little parentheses in the union symbol. The range, okay, let's see. We had that function having a local minimum at 2, or local minimum of 2 at x equals -1, and a local maximum of -2 at x equals +1. The x values don't affect things. And we saw from the graph, we got everything less than or equal to -2 out, and everything greater than or equal to +2 out. Let's go back and look at the picture. -2 and less, yeah, we got all those y values out. +2 and greater, we got all those y values out. So everything from -∞ to -2, including the -2, that's where that local maximum was, and everything from 2 to infinity, including the 2, that's where that local minimum was. These were the 2 black points on the graph of the function at x equals -2 and y equals -2 and y equals 2. X equals ±1, I think it was. Yeah, ±1. Intercepts. So we look for intersections with the x and the y axis. Going back, no intercepts. Never intersects the x-axis, never intersects the y-axis. It gets close to the y-axis, gets asymptotically close to the y-axis, but it never intersects the y-axis, so no intercepts. Horizontal asymptotes. Well, it's got an oblique asymptote, not a horizontal asymptote. No horizontal asymptotes. We'd have to have it level off on the left and the right. If it had a horizontal asymptote, it does not. It actually has an oblique asymptote. So we'll have to deal with that in part E. Vertical asymptotes, yeah, as we observed, the y-axis, and another name for the y-axis is x equals 0 as a line, a vertical line. It gets arbitrarily close to the y-axis. It moves upwards from this side and downwards from this side, though they didn't ask us for that level of detail. But that's sufficient to say we have a vertical asymptote of x equals 0. Okay, so no intercepts because there's no intersection with the axes. There's no horizontal asymptote because there's an oblique asymptote. It can't have both horizontal and oblique asymptotes. We see the y-axis is a vertical asymptote. The y-axis, another name for that, is the vertical line, x equals 0. Let me emphasize it's the line x equals 0, not the x value 0. To be verbally clear on what's going on there. And they wanted to know the oblique asymptotes. Well, they gave us a point on that oblique asymptote. They actually gave us 2 points. They gave us the origin and the point -1, 1. Let's go back and look at the picture again. Passes through the origin and the point -1, 1. So we can figure out the equation of this line. Its slope may be rise -1, run 1. rise over run, it's got slope -1. It passed through the origin. We could use that point to determine the equation of that line using maybe the point slope form or sorry, slope intercept form it looks like we've used, but the slope is -1, as we can see from the picture, as we can compute if you'd like, but trying to develop a degree of maturity on this stuff. The slope's -1. The y-intercept is 0, it passed through the origin. So the equation of that line is y equals -x, and that's the oblique asymptote. So easy enough taking a graph and reading off those ideas. Maybe not so easy being given an equation and producing those ideas. So that'll be the goal, is to find where the vertical asymptotes are, find what the horizontal asymptotes are, find what the oblique asymptotes are for rational functions. So that'll be the plan in the rest of this section, using that information to graph. We'll take on in the next section. We can find asymptotes largely based on the facts that, first, for x large, be it positive or negative, 1 over x is small. And for x positive and near 0, 1 over x is large and positive. For x negative and near 0, 1 over x is large and negative. So the reciprocal of a little number is a big number. The reciprocal of a big number is a little number. And a number and its reciprocal have the same sign, be it positive or negative. There's a synopsis of what's said there. Theorem 2.2.a tells us where to find vertical asymptotes of a rational function. So this offer only valid for rational functions. Beware of that. There's a lot more functions out there than rational functions, but these are commonly used functions. A rational function r of x equals p of x divided by q of x in lowest terms. That is, you canceled all common factors with appropriate care between p and q. Such a rational function will have a vertical asymptote x equals r if r is a real zero of the denominator q once the thing is put in lowest terms. That is, if x minus r is a factor of the denominator q in the rational function p of x divided by q of x in lowest terms. So vertical asymptote will be x equals r in that case. So we'll deal with these by factoring numerator and denominator, canceling common terms with care, and then seeing where the denominator is 0. Let's look at number 44. Okay, rational function, x minus 4 divided by x. We'll graph it using transformations. Use the final graph to find the domain and range and any asymptotes. Okay, so this is rather similar to the other one. Let me say this. Where do you think those asymptotes are going to be? Where do things go wrong? This is a rational function in lowest terms. I mean, this is an x minus 4 term divided by the x term, so there's nothing to cancel. There's no common factors in the numerator and denominator. Of course, you can't cancel those x's. Where's the denominator? 0, at x equals 0. Then, by that theorem we just stated, I bet you that's a vertical asymptote. I bet we have a vertical asymptote of this at x equals 0. All right, they ask us to graph it. That means we'll have to go to the library of functions, find something that looks like this, or maybe change the form of this and find something that looks like that changed form, and then use transformations. All right, so x minus 4 over x. Let's put the x into each of those terms in the numerator. X divided by x equals 1, provided x is not 0. And then we've got, if you like, minus 4 times 1 over x, or minus 4 divided by x. I want to write it like that because that catches my eye. 1 over x, that's in our library of functions. So we'll rewrite the given function in this form. Notice x is not 0 still. X equals 0 is disallowed because that would give division by 0. Let's take the 1 over x function, then we'll multiply it by -4. Well, maybe we'll multiply by 4 and then take a negative. Let's see how we wrote it up. But that corresponds to a stretching and some type of reflection, and then we'll add 1 to it to get a reflection. So start with the library of functions graph, y equals 1 over x. Let's multiply by -1 first. That'll give us y equals -1 over x. Okay, we've taken the function f of x and multiplied it by negative in the terminology back when we were dealing with transformations. This produces a reflection about the x-axis of the original graph. And this is closer to this. We got the negative sign in first. Next, multiply all function values by 4 for the previous function, this function here. So we'll multiply everything by 4, producing y equals 4 times -1x, or -4x. We're multiplying function values by 4. This corresponds to a vertical stretch by a factor of 4. I never like the stretches. They're hard to illustrate in terms of the graphs, but we'll draw some pictures of the stretching. And we ought to illustrate it at some point. Finally, we're missing, let's see, we left off here. We're missing the 1. So we'll add 1 to this. Add 1 to all function values to get -4 over x plus 1, or equivalently 1 minus 4x, and that's the r of x function. Adding 1 to function values is a vertical shift up by 1 unit of the previous graph. So 3 steps. So the graph of the given function results from taking the library of functions graph, y equals 1 over x, and reflecting it about the x-axis. That's the introduction of the negative sign. A vertical stretch by a factor of 4. That puts us in this condition. And then a vertical shift by 1 unit, and that produces the final version of the function. Okay, so we'll start with the 1 over x function on the next slide, and then we'll do these 3 things to it. Y equals 1 over x. It's in blue. Actually, it's the shape of a hyperbola, but it's in blue in the 3rd quadrant and the 1st quadrant. First step was to reflect that about the x-axis. We replaced function values with their negatives. So imagine taking this 1st quadrant piece and reflecting it about the x-axis. This part, reading from left to right, will produce this part, reading from left to right. Down here, reading from left to right, starts over here and moves onward to the right, will reflect about the x-axis to produce this piece in green. Still a hyperbola, it's just a mirror image. We reflected about the x-axis. Had we reflected about the y-axis, we'd actually get the same graph. But we've done this by reflecting about the x-axis. Next, we're going to take the green graph and multiply it by -4. So take the green graph, multiply it by, multiply by 4, +4. We took care of the negative already. So we'll take all the y values on the green graph and stretch them by a factor of 4. That produces this orange graph. Now, it's excuse me, hard to see that that was actually stretching by a factor of 4 just by looking at the graph. But let's track some key points, I think the book called them. This point, -1, 1, right there. Well, if you're going to scale that by a factor of 4 in the y coordinate, that's going to move to the point 1, 4. So we should have the point 1, 4 on the orange graph. Sorry, -1, -1, 4, and we do. So we've taken all these points and shifted them upward by a factor of 4 to produce the orange graph. These that were really close to the x-axis over here, they're 4 times further away from the x-axis in the orange graph. To the best of my ability, I did not use software to graph this. I kind of eyeballed it and guessed. Actually, I probably used PowerPoint to create this. And we'll have the same kind of behavior over here on the little shape in the fourth quadrant to produce the orange curve. Over here, we had the 0.1, -1. We're going to multiply that by 4 in terms of y values to get the 0.1, -4. And indeed, that point right there is on the orange graph. And then similarly, the stretching by 4. The orange graph, by the way, still has horizontal asymptotes of y equals 0. Finally, we're going to take the orange graph and add 1 to it, shift it vertically upward 1 unit. So I'll just take this, shift it upward 1 unit, take the orange one over here, shift it upward 1 unit, adding 1, vertical translation by 1, up. And that produces the red graph. Oh, that means the orange graph had this asymptote of y equals 0. The red graph, the function r that we're dealing with, will have this horizontal asymptote of y equals 1. The asymptote got moved up by 1 in the last step. Vertical asymptote actually never changed. Got the dotted lines to indicate the vertical asymptote. And in red, we have the graph we were looking for, and its asymptotes also graphed in red, so I tried to color code things as best I could. So start with the blue library of functions graph, reflect, stretch, vertically translate. So the graph of the function we're dealing with is as given in red. Let's see, we really moved it up by 1. If we follow this 0.11, this key point, let's see, that rotated around, reflected about the x-axis to become the point 1, -1 here. That 1, -1 stretched to become the point, oops, there it is on the orange one, of 1, -4. And then we added 1 to it and shifted it up to the point 1, -3. So by the way, this point here reflected, stretched, and translated ended up right there if we went through and kept up with key points, as the book has talked about in certain settings. So we've got the graph using our translation information. Let's reproduce it on the next slide, just the relevant part. So here's the graph in red that we were interested in. They wanted to know the domain and the range. Okay, domain, what good x values do you have? Looks like everything except for 0, where we've got a vertical asymptote. And indeed, what could go wrong? Division by 0 when x equals 0. So we could have algebraically dealt with that as opposed to dealing with it in terms of looking at the graph. But no matter how you slice it, everything works except for 0. So the domain is all real numbers except for 0. Here it is written in interval notation. What about the range? Well, we're going to get all y values out, except we never get out the y value of 1. As you see from the picture, this is a situation where as we move to the right, this red curve gets closer and closer to this horizontal asymptote, but never gets there. I didn't say that never happens. I said that's not the definition of a horizontal asymptote. With rational functions, the gets closer and closer part will be the case with rational functions, but there's more to life than rational functions. But we do get closer and closer as we move to the right, and you're getting closer and closer as we move to the left to that asymptote as well. Some more exotic things can happen in the middle, but if I look far enough to the right or far enough to the left, there will be a closer and closer behavior. There may be still some getting there at some point, but the closer and closer part for rational functions and horizontal asymptotes, that will hold if you input large enough x values or large enough negative x values. But horizontal asymptote here, a function never takes on the value 1. So the range is all real numbers except for 1. Same format, we'll go through, remove the point 1, and then union these two disjoint pieces together. Do you believe this is never 1? Yeah. The only way y could equal 1 is if this term were 0, and this term can't be 0. because the only way a quotient can be 0 is if the numerator is 0, and the numerator ain't 0, it's too busy being -4. So algebraically, there's no way to get 1 out either. And so that gives us the domain and the range. They want no asymptotes as well. Yeah. They want asymptotes. Well, since we've got the graph, we see that this horizontal line, y equals 1, is a horizontal asymptote. And the y-axis, that is the vertical line, x equals 0, is the vertical asymptote. So horizontal and vertical asymptotes with a graph, they're easy enough to find. And we had observed earlier, in fact, I guess it was theorem 4.2.a, in a rational function in reduced form, which this is, where the denominator is 0, is where vertical asymptotes will occur. The denominator is 0 at x equals 0, and sure enough, that's where the vertical asymptote occurs. So this is consistent with that theorem. Okay, we want to try to figure out when is it that it goes down on one side, up on the other, up on one side, down on the other, up on both sides, down on both sides. When do those occur? So we're trying to make a transition from using graphs to creating graphs. And note 4.2.a gives away these kinds of behaviors. If the multiplicity of the 0 that gives rise to a vertical asymptote is odd, the graph approaches infinity on one side of the vertical asymptote and approaches negative infinity on the other side. So odd. Multiplicity is odd, that is, of the factor that produces the vertical asymptote in the denominator, goes up on one side, down on the other. Is that what we just saw? Let's look back at that question. Did we have a factor in the denominator of odd multiplicity? We just had an x in the denominator, x to the 1. 1 is odd. And sure enough, the graph goes up on one side and down on the other. So what we just saw is consistent with this statement where we just had an exponent of 1, a 0 of multiplicity 1. If the multiplicity of the 0 that gives rise to the vertical asymptote is even, then the graph either approaches infinity or negative infinity on both sides. That is to say, it either goes up on both sides or goes down on both sides. What's happening here is a change in sign. Here, the graph changes from negative to positive when you transition through. It looks like x equals 2 in this one. I can't plug in 2. We got an asymptote there if it's a rational function. But when we go from one side of 2 to the other side, the function outputs different signed values. So if it's going downward on one side with negative output values, it must be going upward on the other side with positive output values. Either that or it's going upward on one side and downward on the other side. They reverse the roles, the left and right. That I can't tell from simply the oddness of the multiplicity of the 0 that produces this asymptote. I can't tell if it goes up on one side and down on the other, which side is up and which side is down. I can tell you they're different, they're opposite, up on one side, down on the other, but I can't distinguish between the two, simply given the odd multiplicity idea. We could plug in some numbers and find out. Here, we've got even multiplicity. That's related to the function not changing sign when we go from one side to the other of where the vertical asymptote is. We dealt with this as well when we were talking intercepts, when we were doing polynomials and whether the function crossed or touched the x-axis. Conceptually, same thing. Pictures are different, but the concept's the same. It's positive on both sides. If we had even multiplicity related to the factor that produced this vertical asymptote. Even multiplicity, they both go down. they're both negative on both sides versus positive on both sides. You tell me this results from an even multiplicity factor. I can't tell you if it goes up or goes down just with that information, but I could take some test values and probably figure it out. So this is how we can distinguish between these four possible behaviors when there is, for a rational function, a vertical asymptote. Let's deal with asymptotes in general for a rational function, and we'll do a couple more examples. Consider the rational function. All right, so let's see. Rational functions are ratios of polynomials. Say the numerator has coefficients subscripted a's, the denominator has coefficients subscripted b's. Say the numerator has degree n and the denominator has degree m. Then the degrees m and n affect what kind of asymptote you have, if any asymptotes at all. If n is less than m, so the degree of the denominator is bigger than the degree of the numerator, as it says, the line y equals 0 is a horizontal asymptote. That should make sense. That means when you plug in big X values, the denominator is going to be a lot bigger than the numerator if m is greater than n. You're dividing by a relatively large number, and that's the reason the quotient is close to 0. All this asymptote stuff is related to closeness in some sense. So there's an algorithm to go through and look at a rational function and determine horizontal asymptotes. If the degrees are the same of the numerator and the denominator, the line y equals a sub n over b sub m is a horizontal asymptote. So you can tell by looking at, if the degrees are the same, you can look at the ratio of these leading coefficients, a sub n to a sub n, if the degrees are the same. And that gives a horizontal asymptote. So there's the cases under which you get a horizontal asymptote, the line y equals 0, or the line y equals ratio of coefficients. If n equals m plus 1, n was the degree of the numerator, and m was the degree of the denominator. So the degree of the numerator is 1 more than the degree of the denominator. For example, this might be degree 2, and this might be degree 1. This might be degree 7, and this be degree 6. Numerator is 1 degree higher than the degree of the denominator. In a rational function, this conversation only applying to rational functions. In that case, we get an oblique asymptote, y equals ax plus b. This oblique asymptote can be found using long division. So we'll go through and illustrate that, where we actually do the division and see what line results. We'll have a line and a remainder when we do the long division. The line part will give us the asymptote. And that just leaves the case that the numerator is greater than or equal to m plus 2. If that's the case, then there's no horizontal or oblique asymptotes. I can tell you the n behavior in this case, the n behavior is the graph of y equals a sub n, b sub m, x to the n minus m. If you did long division, this would pop up in that process of doing the long division in this case. We could talk about these things being some types of asymptotes as well. It's traditional, especially in precalculus, just to look at asymptotes that are lines. So we've got horizontal lines, vertical lines, and neither horizontal nor vertical lines, the oblique asymptotes. Horizontal asymptotes, vertical asymptotes, and oblique asymptotes, but they're all lines. We could do approximations with other curves. Here we've got some kind of power function, it looks like. But in this case, we'll just say no horizontal or oblique asymptotes when we're dealing with this situation. So let's illustrate these with a couple of ideas. All right, find the vertical, horizontal, and oblique asymptotes, if any, for this function here. Okay, we'll just use that note we just stated. It's just algebra. We don't have to graph anything yet. We'll take care of that in the next section. Okay. G of x is a rational function. It's a ratio of polynomials. The numerator, x cubed plus 1. Denominator, q of x, is this stuff here, x squared minus 5x minus 14. There we go. The numerator is degree 3, n equals 3, from the 3 right there. Denominator is degree 2, m equals 2, in the notation we had earlier. So we've got n equals m plus 1, 3 equals 2 plus 1. So this is a situation where we get an oblique asymptote. Numerator is degree 1 greater than the denominator. That means oblique asymptote. How do you find that oblique asymptote? Well, by what we just stated, we'll do long division. So by long division, we'll take the x cubed plus 1 and divide it by x squared minus 5x minus 14. Simply divide this into that. Divide denominator into the numerator. So a little trouble with my fonts making this look like a division sign, but away we go. So what do you multiply this by to eliminate the highest power of x? So multiply it by x. X times this will produce x cubed minus 5x squared minus 14x. Increase the power of x on each by 1. Subtract, parentheses around this, and then subtract. You lose the x cubed. You'll have 0 minus negative 5x squared, becomes positive 5x squared. 0 minus negative 14x produces a positive 14x, and we'll bring the 1 down. How many times does x squared minus 5x minus 14 go into this? Well, 5 times. We'll multiply by 5, produce this, subtract, put parentheses around it, and subtract, we'll lose that. 14x minus a negative 25x is 14x plus 25x, or 39x. 1 minus negative 70, it's 1 plus 70 produces a 71. This is the remainder. Here's the quotient. Here's the remainder. Let's see, here's the divisor. I think this is called a dividend. I don't really remember all those names. This is the thing we're looking for. This is how many times the denominator went into the numerator, and this is the remainder. This, how many times the quotient, they call it as well. This is the oblique asymptote. So we get y equals ax plus b. This is ax plus b. So x plus 5 is the asymptote, and it's an oblique asymptote. How did we know for sure this was going to come out as a first degree polynomial and not some higher degree polynomial? Because we only have an oblique asymptote when the degree of this is 1 greater than the degree of that. So the first step of division, you're going to have some power of x here, and you're going to have 1 larger than that power of x here. This is a 2, x squared. This is a 3, x cubed. If that were an x to the 7th, then we'd have an x to the 8th here, or we wouldn't have an oblique asymptote. And so when you do the multiplication, the first thing you put down is some multiple of x, 1x in this case. And then you perform the arithmetic. You'll only have to take it a couple of steps and produce these terms here. The remainder really plays no role. It's what the quotient is, the x plus 5. So I kind of like finding oblique asymptotes. It's easy. I know when they're there. They're there when the degree of the numerator is 1 greater than the degree of the denominator. If that ain't the case, no oblique asymptotes. And how you find them is long division. And you simply take the quotient, toss the remainder, and that is the oblique asymptote. So finding oblique asymptotes is very mechanical in that sense. All right, so the observation is, just to wrap that one up, G has an oblique asymptote, so there's no horizontal asymptotes. It's too busy having an oblique asymptote. Vertical asymptotes we can still address. By theorem 2.2.a, locating vertical asymptotes, we want to factor this and put it in simplest form. By the way, some factoring could be done with the numerator. It's a sum of two cubes, but I don't think that's going to have any effect in terms of simplifying. Trust me, this is in reduced form. So we need to take the denominator and set it equal to 0. As long as this is in reduced form, it is. So take the denominator, x squared minus 5x minus 14, set it equal to 0. Oops. Can you factor this? So we need two things that multiply to give negative 14 and add to give negative 5. How about negative 7 and positive 2? The product of these indeed is negative 14, and the sum of these is negative 5. So that'll work. FOIL this out, and you'll get that back if you're rusty at factoring. But that factors as x minus 7 times x plus 2 equals 0. So x equals 7 is a problem, and x equals negative 2 is a problem, setting the constituent factors equal to 0. And according to theorem 2.2.a, that's where the vertical asymptotes will be, at x equals negative 2 and x equals 7. I'll write them, left to right in increasing order that they appear on the number line. So there's the vertical asymptotes. Oblique asymptote, well, if it's got an oblique asymptote, it can't have a horizontal asymptote. It can still have vertical asymptotes. In fact, it's got a couple of them, and there's where they are. So we could go attempt to graph this with the information we have now. We put a vertical dotted line at x equals negative 2, a vertical dotted line at x equals 7, and what was that oblique asymptote? Y equals x plus 5, and graph the line y equals x plus 5 in dotted lines. And that'll give us all the asymptotes. And based on that, we probably get a pretty good idea what the graph is if we plotted a few points, strategically plotted a few points, as we'll do in the next section. One last one. A word problem of sorts. That's just going to translate into find the asymptotes of this function. But the story is, a rare species of insect was discovered in the Amazon rainforest. To protect the species, environmentalists declared the insect endangered and transplanted the insect into a protected area. The population P of the insect, T months after being transplanted, is given by this. So population size in terms of months, T, is given by this. Well, it's a rational function. So, of course, I give you rational functions in this section. Part A, how many insects were discovered? That is, what was the population when T equals 0? How many were transferred into the protected area? Part B, what will the population be after 5 years? Oh, these guys. T is measured in months, and they've asked us 5 years. We'll have to convert 5 years into months. So that was sneaky of them. They've mixed units together on this one. Determine the horizontal asymptote of P of T. What's the largest population that the protected area can sustain? Horizontal asymptote will be the largest value that P of T could reach, and it would only asymptotically approach that. But they want to know in part A, what do you get when you plug in 0 months? When this transplanting of insects from one place to another occurred. We'll plug 0 in for T, gives us a 0 here and here, here and here. Use the parentheses as always. That gives us 50 divided by 2, so 25. The units are insects, so it was a population size, so 25 insects initially. Part B, what will the population be after 5 years, according to this model? Well, we got to take 5 years, multiply it by 12 months per year to create 60 months. So the T value we use at 5 years is T equals 60 months, because T is measured in months. Okay, so we'll plug in 60. Get P of 60, you put 60 wherever you see a T, just as we did with the 0, there and there, isolated with parentheses. Do the arithmetic, that comes out to about 596.15 insects. As there is no 0.15 insects, and so we'd round it down to an even 596 insects. So that would be the population 5 years later, well, 60 months later, better yet. And in part C, determine the horizontal asymptote of P of T. horizontal asymptote. So I tell you it has a horizontal asymptote. Is the degree of the numerator and the denominator the same? They are. First degree polynomial, t to the first power. First degree polynomial, t to the first power. When n equals m, in the terminology of that last theorem we saw, that's when you get horizontal asymptotes. So yeah, we're going to get a horizontal asymptote. I think that result even told you how to find it. Numerator and denominator of p are both first degree or degree 1 polynomials. The degrees are the same, is what matters. Then by note 4.2, point B, part 2, so stated as a note, the horizontal asymptote will be the leading coefficient in the numerator divided by the leading coefficient in the denominator. We need to distribute that 50 to see what that leading coefficient is. So we'll take 50 times the 1 plus 0.5t. Distribute, that'll give us 50 times 1. So over here, 50 times 0.5, half of 50 is 25. In the denominator, we've got, let's just rearrange the order on that. So I see the t coefficients here. Here's the constant coefficients. We've written the numerator and denominator in standard form for polynomial. If you don't like that, leave it in the other form. I need to pick off the coefficients of the highest power of t in the numerator and denominator. That's 25 in the numerator and 0.01 in the denominator. A1 and B1 in the notation of what we had earlier are 25 and 0.01 respectively. So we'll take that quotient, and that should be the horizontal asymptote. That's what we were told in that cookbook approach to find asymptotes for rational functions. That's 25 divided by 0.01. That's 25 times 100. So that's 2,500, 2,500. And that must be the horizontal asymptote. So if we graphed this function, then we'd see when t is really big, population size is really close to 2,500. So the largest the population can be is this asymptotic value of 2,500 insects. When t is large, the population will approach this value of 2,500. And I don't know about this model, but these ideas of environments having limits as to how many organisms can be maintained in an environment, it's called a carrying capacity in an environment. We'll deal with a model that mimics this carrying capacity. Some of these original models actually come out of ecology and not so much out of math, but it's called the Logistic Equation, and I think it's the last section we'll cover in Precalculus 1. But this asymptote gives of p equals 2,500 insects, gives us the largest number of insects we could have. The model is going to asymptotically approach that. And that takes care of this section, talking about properties of the graphs of a polynomial. Next, we'll take equations. In the next section, we'll take equations, find these things, asymptotes in particular, and then use those to go through and graph rational functions. So that's where we'll take equations and produce graphs. In this section, you were always given the graph. Well, that's not true. You were given the equation and asked to find some properties of it, but we never graphed anything using those properties. Well, fret not, that's next. So have a nice day. I'll see you in the next section in a little while.